last lecture you have seen the importance of the welding as compared to the other manufacturing process to get the desired size and shape in the component which can be used by us in our daily life or for fabrication of the various machines or their components. Today we will see that the welding processes which are available are many, and each welding process offers the unique advantage. During the welding some of the things which happen are very common. In general the welded joint offers the metallic continuity between the members to be joined, and for this purpose to obtain the metallic continuity various approaches are used, and each welding process is based on the use of a specific approach. For example, for obtaining the metallic continuity between the members to be joined, the edges of the fixed surfaces are brought to the molten state, and thereafter solidification of the weld metal results in the continuity of the material and produces a weld joint. So, here the application of heat for melting the fixed surfaces is important, and this there can be different sources which can be used to apply heat, and in the different processes like in electron beam high velocity beam of electrons is used, like in laser beam a beam of laser is used, and in arc welding processes arc heat is used for melting the fixed surfaces and to get the metallic continuity in form of the weld joint. Similarly, in some other processes only the fixed surfaces are brought to the molten state and get a metallic continuity in form of the weld joint, but the filler material is not added from outside. So, those processes in which the filler material is added from the outside, they behave in different way, their approach is different as compared to those in which filler material is not used. Similarly, there are certain processes in which in addition to the heat, pressure is also applied to consolidate the members and get the weld joint which can serve the purpose. Since the processes, there are many welding processes, each process offers a specific set of the conditions under which weld joint is made, and therefore, it is worth to look into the fundamental way by which these processes can be grouped in different ways, and that is why we will see that what are the different possible ways through which the welding processes can be grouped and classified. But before going into that, it is important to see that what is the need of classifying the welding processes. So, here this slide shows the various the components which will be covered in this presentation. The first starts with the need of the classification, and then the basis on which the welding process can be classified as a welding with or without filler material, the welding using the variety of sources to apply energy during the welding, and the welding based on the arc or welding without use of arc, or welding where fusion takes place, or welding where processes where only pressure or mainly pressure is applied to get the weld joint. So, these are the various parameters or the factors on the basis of which we will try to classify the welding processes. We will also try to comment critically on the way by which each criteria helps to classify the welding processes and the deficiencies related with that particular criteria. So, as far as need is concerned, for classifying the welding processes, it helps us to group the various processes based on the fundamental similarity in the nature, like those processes in which the weld joint is obtained by applying the heat to melt the fixed surfaces only, or by using the high temperature just to soften and then apply pressure to get the metallic joint, or just applying the high temperature and getting the metallic continuity through the diffusion. So, there are certain the basic features, basic mechanisms through which the weld joint is developed, so that if we try to group the various processes, the way by which the weld joint is made can help us in understanding the welding processes in better way. So, further, when the welding processes are classified based on the fundamental similarities or separated based on their dissimilarities in nature, it helps us to have the better understanding of the each process, and it also helps to make the communication regarding the welding processes and its feature easier by having just one name for each of the process. Like arc welding process, in under the arc welding process category, we have many names related with the arc welding process, like submerged arc welding, where arc is submerged under the flux, or metal inert gas arc welding, where consumable filler is used to develop the arc, and the arc is covered by the inert gas, or sealed metal arc welding process, where consumable arc is developed between the consumable electrode and the base metal. So, when the processes are classified under one particular heading, it helps to make the communication regarding the welding process easier, and further it helps to organize the information about the welding processes in better way, like what are the arc welding processes, what are the processes and in which only the fusion and thereafter solidification helps to get the metallic continuity in form of the weld joint, or what are the processes in which a pressure helps to get the metallic continuity and obtain a weld joint. So, when the welding processes are grouped and classified on the basis of their the different parameters, this helps to organize the information about the welding processes in better way. Further, the grouping based on the fundamental natures related with the welding processes also help in naming the new processes which are being developed, or the hybrid processes which are being developed by the researchers and technologists to deal with the difficulties associated with the existing and the conventional welding processes. So, when the welding processes are classified based on the various factors related with the processes, it helps us in understanding the processes better, it helps us in communicating and organizing the welding process in better way. So, this is how we can say that classification of the welding processes is important in understanding the welding process in better way. So, the first parameter or the criteria based on which welding process we can classify those welding processes where to get the metallic continuity, whether we use the filler material or not. So, whenever we use filler material, it is also brought to the molten state and used to fill the gap between the components to be joined. So, based on this criteria, the welding processes can use the filler material, or they may not use any filler material. So, when the welding processes do not use any filler material, means the welding process without filler material, those the weld joints are called autogeneous weld joints. These processes mainly cause the melting of the base material only, and thereafter solidification of the molten base material results in the metallic continuity. And under this category, we have the fusion welding processes, where the edges of the plates to be welded are brought to the molten state. Subsequently, their solidification results in the metallic continuity to produce a weld joint. Similarly, these processes where no filler material is used, solid state welding processes like the friction welding, spot welding, or ultrasonic welding and explosive welding, where the metallic continuity is obtained without addition of the filler material. So, those processes where no filler material is used and the two components to be joined are welded together either with the application of heat or with the application of heat and pressure both, or only application of the pressure. This results in the autogeneous welds. So, those welding processes we can say are result in the autogeneous weld, where filler material is not used. Those welding processes where filler material is used for especially in cases of when the thick sheets are or thick plates are joined. These welding processes involve the melting of the base material and the filler material both, and when it is done, means when the filler material is used to get the metallic continuity between the members to be joined. There can be two situations when the filler material is having the composition similar to that of the base material, or it can have the different composition. So, when the composition of the filler material is similar to that of the base material, we call homogeneous weld, where composition of the filler is similar to that of the base material, and we get the heterogeneous weld when the filler material composition is different from the base metal. But in both these groupings, whether it is homogeneous weld or heterogeneous weld, the filler material is used, and filler material is brought to the molten state along with the base material's fin surfaces to get the metallic continuity and get the weld joint. So, those welding processes in which the fusion takes place, but the filler material is not used. So, this is the first category where filler material is not used, but the fin surfaces are brought to the molten state to get the metallic continuity and to produce the weld joint. These processes are mainly the gas welding, the gas tungsten arc welding, the plasma arc welding, electron beam welding, and the laser beam welding. These processes are basically different in the way by which heat is generated, and because in the gas welding the source of the heat in these welding processes is different, but in all these cases there is with the thin sheets, when welding thin sheets, the filler material is normally not used. The gas welding process use the chemical reactions for generating the heat through exothermic reactions, while in tungsten gas tungsten arc welding, the heat required for melting the fin surfaces of the component to be joined is obtained through the arc between the tungsten electrode and the base material, where arc is well covered by the inert shielding gas or the gas which can effectively protect the weld pool from the atmospheric contamination. While in case of the plasma arc welding, the plasma is generated either between the electrode, tungsten electrode and the nozzle, or the plasma is generated between the tungsten electrode and the base material, and this the plasma provides the heat required for melting the fin surfaces and get the metallic continuity without adding any filler material. Similarly, electron beam welding process, heat required for melting the fin surfaces is obtained by applying a high velocity electron beam in vacuum. The component is brought to the molten state through the beam of the electrons hitting to the fin surfaces and generating the heat. Similarly, in the laser beam welding process, heat required for melting the fin surfaces of the thin sheets without use of filler material is obtained by applying the beam of laser, and this can be performed even under the atmospheric conditions, but the electron beam welding requires the vacuum, because beam of electron when moving through the atmospheric air in the ambient condition, the velocity is reduced very significantly, and the beam is not able to generate heat enough to produce to bring the fin surfaces to the molten state and to produce the weld joint. So, in all these welding processes there is a difference in the way by which heat is generated, but since the filler material is not used while using these welding processes, especially when welding the thin sheets. That is why these are categorized under the fusion welding processes without filler material. So, in these welding processes where just the melting of the Fing surface is carried out without addition of the filler material, solidification normally starts from the Fing surfaces or from the fusion boundary without any nucleation stage. The partially melted grains of the base material starts to grow directly and produces a weld joint. So, here primarily it involves the growth mechanism without nucleation stage, which is called epitaxial solidification. So, those situations where either only the base material is brought to the molten state for developing a weld joint like in our autogeneous weld, or those situations where filler material composition is similar to that of the base material, the solidification normally takes place directly by the growth mechanism, where partially melted grains start to grow directly without the nucleation stage, and this type of the solidification is called the epitaxial solidification. While in those situations where the filler material composition is different from the base material, the solidification requires the two stages. First the nucleation of the grains and thereafter their growth to complete the solidification sequence and produce weld in solid state. So, the solidification in the heterogeneous weld where composition of the filler material is different from the base material takes place in the two stages. If we see in those situations where the filler material is not used, but the base material itself is having very wide solidification temperature range, those weld joints, those autogeneous weld or homogeneous weld are found to be sensitive for the solidification cracking, because lot of residual stresses are set in along the weld center line, and that increases the cracking tendency along the weld center line and results in the solidification cracking. Solidification cracking is called so because it occurs just at the terminal stage of the solidification or just after the completion of the solidification, as soon as high residual stresses set in along the weld center line and leads to the cracking. So, to overcome this problem of the solidification cracking, various methodologies are used to change the grain morphologies even in the autogeneous weld and the homogeneous welds, if the change in composition of the base material is not possible. And apart from the use of the fusion welding processes, some solid state welding processes like friction welding or friction stir welding process can also be used if the solidification cracking is a major problem in case of the fusion welds where filler material is not to be used. Now, we will see the welding process where filler material is not used, but they are carried out in the solid state without fusion of the Fing surfaces. In the previous sets, we have seen that the fusion of the Fing surfaces is done, but no filler material is used, and in these welding processes there are certain welding processes where filler material is not used, but the weld joint is performed in the solid state itself. And these can be used for thin as well as thick plates by applying the heat and the pressure, and this the various approaches are used for developing the weld joint in the solid state or in the semi solid state. For example, in the friction stir welding, material is heated by the frictional heating to about 300 to 400 degree centigrade, where thermal softening of the material like in aluminum, in case of aluminum sheets softens the base material, and the mechanical churning along the edges results in the consolidation of the metal and forms a weld joint even in the solid state. and in this case no melting takes place, maximum temperature goes in case of aluminum to around 300 to 400 degrees centigrade. Similarly, in resistance welding process, material is softened first by the electrical resistance heating, and then pressure is applied to consolidate the weld joint, to consolidate the joint at the interface and produce the metallic continuity for producing a weld joint. In explosion welding, the high velocity of one of the members to be joined is obtained by putting in the explosive material over it, and then high velocity plate allowed to move in a specific way and hit the another member under certain control conditions to get the metallic continuity. In this process, the joint is mainly formed by the mechanical interlocking at the interface, while in ultrasonic welding process the joint is obtained under very low temperature conditions without addition of the filler material, and the required frictional heat is obtained by supplying the ultrasonic vibrations at the interface through the suitable ultrasonic welding device, and that helps to generate the minor frictional heat, at the same time leads to the mechanical interlocking and the diffusion at the interface to produce the weld joint. In all these welding processes, if we see, the material is not brought to the molten state. However, in resistance welding there may be semi solid state condition, but the pressure is used to consolidate the things, but no material is added from outside, and that is why all these welding processes are generally carried out under the solid state or semi solid condition, where the filler material addition is not done, and these welding processes include the friction stir welding, resistance welding process, explosion welding process, and ultrasonic welding processes. You will see now some other welding processes where fusion is carried out and the filler material is used. In these processes, these processes are inherently designed to produce a weld joint by applying heat for melting the base material and the filler material both, so that weld metal can be applied in the places where it is required, and the continuity metallic continuity can be obtained to produce the weld joint. So, these processes like shielded metal arc welding process or metal inert gas welding process or submerged arc welding process, the nature of the process itself is such that the electrode arc is developed between the electrode and the base material, and the arc helps to melt the base material and the filler material both simultaneously, and helps to deposit the material from the base filler material into in the groove between the base materials, and to get the metallic continuity and to produce the weld joint. These fusion welding process with filler are normally used in case of the thick plates, usually greater than the 5 mm, and this process also offers the higher deposition rate than as compared to those processes where filler material is not used. For example, TIG we can use with both filler material or without filler material, but because of the low heat input which is possible with the TIG process itself, this cannot the TIG does not offer the higher deposition rate. So, those processes which are designed to melt with the heat of the arc or with the heat source which is being used along with the base material usually offers the higher deposition rate than other processes, and these the processes are normally used for joining the plates of thickness greater than 5 mm. These processes are metal inert gas welding process, submerged arc welding process, flux cored arc welding process, and electro slag and electro gas welding process. In all these welding processes, in the first 3 if we see some arc is generated between the consumable electrode and the base material, and it is covered by the inert gases. In case of metal inert gas, it is covered by the flux all around the arc for protecting the weld pool, while in case of flux cored arc welding, arc is covered by the inactive gases that are generated by the decomposition of the flux within the electrode during the welding. In case of electro gas and electro slag welding process, the heat required for melting in case of electro slag is obtained by the electrical resistance heating, while in case of electro gas welding process, the arc is established between the weld pool and the electrode, and it is well covered by the shielding gases. In all these processes, deposition rate is generally high deposition rate is used. For example, submerged arc welding process can be used for welding up to 1 inch or 25 mm thick sheets in single pass, while further thicker sheets can be effectively welded using the electro slag and electro gas welding process. Even up to 300 to 400 mm thick sheets, thick plates can be welded using electro gas welding process. So, if we see the variety of welding processes which are available for developing the weld joints, and try to see that how effectively we can classify these welding processes based on the factor, based on the way whether we are using the filler material or not. If we see here, the gas welding processes was the only fusion welding processes earlier in which joining could be achieved with or without filler material, and the gas welding process performed without filler material was termed as a autogeneous weld. So, initially when the gas welding process was used without addition of the filler material, those weld joints were termed as autogeneous weld joints, but this process can also be used for can be used with the filler material also. If we see here, with the development of the tungsten inert gas welding process, electron beam welding process, laser beam and many other welding processes, such a classification created confusion, because all these processes can work with both filler material or without filler material. So, this classification in that way does not help much to group the processes effectively, because some of these processes can be used with both with the filler material and without filler material for developing the weld joints, and this has led to the classification of the weld joints based on some other factors. So, the next parameter based on which the welding process classification we can see is the source of the energy being used for developing the weld joint. So, this source of the energy mainly is used for how the heat is generated or how the metallic continuity is obtained. So, on the basis of the energy being used for developing the weld joint, based on this factor we can classify the weld joints in the different ways. For example, how the energy is being generated, how the heat is being generated for developing the metallic continuity or the bond between the components to be welded. So, based on the type of energy being used for developing the metallic bond between the components to be welded, the welding processes can be grouped under the 4 headings. For example, those processes which use the chemical energy to generate the heat and get the metallic continuity to produce the weld joint, or those processes which use mechanical energy to get the metallic continuity between the members to be joined, and similarly those which use electrical energy to get metallic continuity between the members to be joined, or the radiation energy. So, there are different processes which use the different types of the energies. So, these now efforts will be made to see that how these processes can be grouped under the chemical energy, those processes which are using chemical energy, mechanical energy, electrical energy or the radiation energy. So, the first criteria say chemical energy based, those processes which use chemical energy for developing the heat required for melting the fin surfaces is obtained from the chemical reactions. For example, these welding processes which use the chemical energy for developing the heat for melting the fin surfaces are the oxy-fuel welding processes or thermite welding processes. In the oxy-fuel welding process, hydrocarbon gases are burned with the oxygen, and the heat generated so is used for melting the fin surfaces and get the metallic continuity after the solidification. While in case of the thermite welding, the chemical reactions are used to get the filler material in the molten state, and then it is supplied between the members to be joined. So, in both these processes, chemical reactions, exothermic chemical reactions are used for generating the heat required for melting the fin surfaces or to get the filler material in the molten state and supply it to the between the components to be joined for getting the metallic continuity. So, these process now another another type of energy based on which we can classify the welding processes, the mechanical energy. Those processes which use mechanical energy either to develop the frictional heat or to cause plastic deformation so as to get the metallic continuity to produce a weld joint. So, in these processes somehow the mechanical energy is applied between the members to develop the frictional heat or to cause the plastic deformation so as to get the metallic continuity. In these under this category we have the ultrasonic welding, where ultrasonic vibrations are applied at the interface through the components to be joined, which helps to develop the marginal frictional heat as well as leads to the mechanical interlocking to develop the weld joint. While in frictional welding, friction welding, the friction the components to be joined are subjected to have the relative movement between them under the normal pressure. So, the frictional heat generated is used to soften the fin surfaces, and then finally forging pressure is applied to get the weld joint. While in friction stir welding, the tool pin and shoulder, a tool having the pin and shoulder is rotated at a high speed and forced to pass through the plates to be joined. This results in the frictional heating of the edges to be joined, their softening, and finally the churning of the edges to be joined, and then consolidation or mechanical forging helps to get the metallic continuity between the members to be joined. While in case of explosion welding, high kinetic energy is imparted to one of the members to be joined using the explosive, and the movable plate is guided and allowed to move through in very controlled way, so that it hits to the another member in very controlled positions at particular angle, so that the metallic continuity between the members to be joined is obtained primarily through the mechanical interlocking. So, if you see these the welding processes where the mechanical energy is being used, mechanical energy is primarily used to develop the heat through the friction, and subsequently the plastic deformation at micro level at the interface results in the mechanical metallurgical bond between the members to be joined and produce a weld joint. The electrical energy is another energy which is very commonly used in the welding processes, and those welding processes using electrical energy to produce the heat for developing for developing a weld joint, like the welding processes which use the electrical energy to produce the weld joint includes the arc welding process, resistance welding process, electroslag welding processes, and electro gas welding process. Although there are many other processes which use the electrical energy to generate the other to generate the energy in other forms like electron beam or the laser beam process also use the electrical energy to generate the laser and electron beam, and these are used subsequently for melting the fin surfaces of the base material and get the weld joint. So, in these processes electrical energy in arc welding process is mainly used to establish the arc between the either non-consumable electrode like in tungsten inert gas welding process or between the consumable electrode and the workpiece. So, the heat generated by the arc is used for melting the fin surfaces and get the metallic continuity when using the electrical energy to generate the arc. While in case of resistance welding processes, electrical energy is mainly used to generate heat through the electrical resistance heating principle, where I square R T I square R T formula is used to find out that how much heat is being generated at the interface, where R stands for the contact resistance at the interface, I is the welding current that is being used, and the T is the time in seconds for which heat is current is applied to generate the heat. So, mainly heat in resistance welding process is generated through by supplying the electrical current through the components to be joined, and high electrical contact resistance at the interface develops lot of heat, which helps to soften the interface between the members to be joined, and subsequently the application of the pressure results in the development of the weld joint. In case of the electroslag welding, heat required for melting the fin surfaces is obtained through the electrical resistance heating, where current is passed through the slag and the molten weld pool between the consumable electrode and the base material. So, basically electrical resistance heating helps to melt the base material continuously and to produce the weld joint after the solidification. In this process, the electrical resistance heating basically takes place by the flow of current through the molten slag and the molten weld metal, and the current is supplied through the consumable electrode, and the workpiece is made part of the electrical circuit. So, here electrical current electrical energy is used to generate the heat through the electrical resistance heating and to get the base material fin surface in molten state, and also use the same energy for melting the filler material, that is the consumable electrode. Similarly, in case of the electro gas welding process, heat required for melting the fin surfaces and filler material is obtained by establishing the arc between the consumable electrode and the weld pool. So, here the arc is well covered by the inert or inactive gases to protect the weld pool from the atmospheric contamination. So, in all these welding processes, we see that the electrical energy is used for melting the fin surfaces by generating the heat through the different mechanisms, whether it is development of the arc or through the electrical resistance heating, or the electrical resistance heating in case of electroslag welding also, or by using the arc between the consumable electrode and the weld pool in case of electroslag welding. So, we can see that these there are certain processes which use the electrical energy primarily to produce heat, so that the weld joint can be obtained. There are certain processes which use the radiations to get the fin surfaces in the molten state and get the weld joint. These processes use the electromagnetic radiations for generating the heat so as to develop the weld joint. One is laser beam welding and another is electron beam welding process. In the laser beam welding, mainly laser is directed towards the workpiece surface to be workpiece members or the members to be joined. Here it is important that beam diameter plays a significant role in bringing the edges of the components to be joined to the molten state. So, if the beam diameter is very small, then the gap between the plates to be joined is to be very fine, and the edges of the plates must be straight, otherwise beam will pass through the gap between the plates to be joined. So, especially when using the laser beam of very small diameters, say of 100 micron or 200 micron, the edge preparation becomes very critical. Otherwise, if there is any lack of the straightness or the roughness presented the edges of the plates to be joined, then the beam will pass through the gap between the plates and the melting will not occur. Similarly, in electron beam, the beam of the electron is directed towards the edges to be brought to the molten state to be and the edges of the components to be joined are brought to the molten state by directing a beam of electron which are moving at very high speed, and impact of these electrons moving at very high speed with the edges of the surfaces of the component to be joined generates lot of heat, and which helps to bring the feng surfaces to the molten state. And but this electron beam welding process requires a vacuum because electron beam and the electrons cannot move at high speed in the ambient conditions because of their collision with the atmospheric gases and the molecules. That is why it is mandatory to have the electron beam mandatory to have the vacuum in case of the electron beam welding processes. But if we see here, as far as this classification is concerned, the radiations in form of the laser beam and the electron beam welding processes or electron beam are used for melting the edges of the component to be joined together and get the metallic continuity to produce the weld joint. So, if we have to comment on this way of the classification of the welding process, where the classification is based on the kind of energy which is used for developing the metallic continuity. If we see, we have seen that the energy in various forms can be used for developing the weld joint, like chemical energy, electrical energy, the laser in form of light or sound or ultra or the mechanical energies can be used for developing the weld joints. However, except the chemical energy, all other forms of the energies are generated from the electrical energy. So, whether it is the mechanical energy where vibrations or ultrasonic vibrations are applied, or the electron beam or laser beam is used, in all these forms are generated, means energies of all these forms, whether it is mechanical, light or electron beam, these energies are generated from the electrical energy for the welding purpose. So, except the chemical energy, all other forms of the energies are generated again from the electrical energy. So, in this way this classification becomes slightly confusing. Hence, the categorization of the welding processes based on the form of the energy criteria is not very properly justified. So, except the chemical energy, because in all other forms of the energies are using the electrical energy and that is why this classification based on the form of energy is not very effective and properly justified. So, the welding processes we can further classify based on the presence or absence of the arc which is used for generating the heat required for developing the weld joint. So, the criteria on the basis of which we can classify whether the arc is developed or not. This classification is based on the fact that whether our welding arc is generated for producing a weld joint or not. So, here welding arc is mainly used for generating the heat required for melting the fin surfaces, so that metallic continuity can be obtained either with the use of the filler material or without use of the filler material. So, based on this we can classify as arc welding processes or non-arc welding processes. In the arc welding processes, arc is established either between the consumable electrode and the base material, or arc is established between the non-consumable electrode and the base material. So, if the arc is established between the consumable electrode and the base material, in general we get the higher deposition rate and the higher productivity, while in case of those processes where arc is established between the non consumable electrode and the base material, like in gas tungsten arc welding or in plasma arc welding processes, the deposition rate is usually low and the filler material is added, either filler material is added from outside or the filler material is not added for getting the weld joint. While in case of the non-arc welding process, heat required, either heat is generated through the chemical reactions or through the frictional friction, or the joint is made using the mechanical interlocking or developing the pressure for causing the plastic deformation, or through the diffusion or other mechanisms. So, those welding processes where arc is not used for developing the weld joint and get the metallic continuity, they are called as non-arc welding processes, and where arc is used for generating the heat required for melting the fin surfaces to get a weld joint are called the arc welding processes. So, here we will see first the non-arc welding processes. These processes primarily use pressure with or without heat. So, these processes use pressure or heat either in singly, means only heat or only pressure, or combination of the both to get the weld joint. So, heat in these non-arc based welding processes, if it is used, can be generated using the electrical resistance heating principle or using the exothermic chemical reactions or frictional heat. These are the three ways through which heat can be generated in the non-arc welding based processes. There are other ways through which also heat can be generated for melting the fin surfaces and developing the weld joints, like electron beam and the laser beam. So, in these processes we can use pressure in combination with the heat or without application of heat to get the weld joint. Well, the heat, if the heat generation is involved, then electrical resistance heating, exothermic chemical reactions and the frictional heating or some radiations can be used for generating the heat required and to get the metallic continuity. So, these welding processes where arc is not generated, but the heat required for for developing the weld joint is obtained through the resistance heating, electrical resistance heating, like in resistance welding processes. Arc is also not generated in gas welding, because here heat is obtained through the chemical reactions between the oxygen and the hydrocarbon fuel gases, and in thermite welding the chemical reactions between the aluminum oxide, magnesium oxides and the iron mixture is used for having the chemical reactions which are exothermic in nature and can generate lot of heat for melting the filler material. Similarly, in ultrasonic welding, there is no arc and the required frictional heat is obtained through the mechanical energy in form of the ultrasonic vibrations, while in diffusion welding absence of arc is also there, but here the metallic continuity is obtained by the diffusion through the interface between the members to be joined, and for this the component to be joined are kept under the firm metallic contact at high temperature for long under pressure, so that the diffusion across the interface can take place from one side to another, and they get a metallic continuity. Similarly, in explosive welding, there is no arc, and the joint is obtained through the mechanical interlocking by moving the one plate or one component to be welded at a high speed with respect to another, and the impact results the mechanical interlocking at the interface and produces a weld joint. So, in all these welding processes, if we see, the heat is generated through the various means like resistance heating, chemical reactions, again chemical reactions, or the diffusion, and the ultrasonic vibrations, or the kinetic energy between the kinetic energy by impact of the high velocity moving component against the another member with which it is to be joined under the explosive welding category. So, here while are those processes in which heat required for melting the fine surfaces and get the metallic continuity is obtained from the welding arc. In these processes, arc is invariably part of the welding process for generating the heat, and heat generated is used either for melting the fine surfaces or for melting the filler material and the fine surfaces both to get the metallic continuity. For example, in sealed metal arc welding process, the arc is established between the consumable electrode or shielded electrode and the base material, and the heat generated by the arc is used for melting both consumable stick electrode and the base material, and development of the weld pool, molten weld pool, and subsequently solidification results in the weld joint. While in case of the gas tungsten arc welding, arc is established between the tungsten electrode and the base material, and the heat available from the arc is used for melting the fine surfaces of the base material, and if the thicker plates are being joined, then filler material can be applied from the outside. Here the filler material is placed in the arc, and then melting of the filler material and getting it mixed with the molten base material results in the metallic continuity, but this filler material in the GTW process is mainly used when the thick plates are to be joined. Similarly, the plasma arc welding process, the arc heat of the arc is used for melting the fine surfaces of the base material to be joined, or for melting the filler material if it is being used, because in both these two welding processes the non-consumable tungsten electrode is used, and therefore to fill, if the large amount of the weld metal is to be applied, then filler metal is used from outside. And in case of gas metal arc welding process, again consumable electrode and the consumable electrode is used, and the welding arc is established between the consumable electrode and the workpiece, and the heat generated by the arc is used for melting both the consumable electrode as well as the base material, and get the weld pool, which after the solidification results in the weld joint. While in case of the flux core arc welding, in flux core arc welding process is similar to the gas metal arc welding process, but with the difference in the sense that the electrode is having a flux filled in the core portion of the electrode, and this the flux decomposes by the heat of the arc and provides the cover or shielding to the arc and the weld pool by the inactive gases. during this flux cored arc welding process. So, heat of the arc generated between the consumable flux cored electrode and the base material is used for melting of both electrode as well as base material, and to so as to produce the weld pool and a weld joint. While in case of submerged arc welding process, the arc is established between the consumable electrode and the base material, and the arc is submerged under the flux pool, and which this flux forms the complete cover around the weld pool and the arc to protect the pool from the atmospheric contamination. So, submerging feature of the arc in this process is different from other welding process. It helps to shield the welding arc and the pool effectively. At the same time, it also reduces the heat losses from the arc to the surrounding, and that is why this process offers very good the penetration and the high deposition rate, and hence used for joining of the thick sheets. So, if we have to look into that how effectively this classification can be used to categorize various welding processes based on the fact whether there is arc or there is no arc. If we see here, the arc and non-arc welding process classification leads to grouping of all the welding processes in one class and all other welding processes in another class. Means those welding processes where arc is generated are kept in one category, and all those welding processes where no arc is generated and arc is used, and they are put in another category. However, there are welding processes where there is a confusion, and there is a presence of both, that arcing for a short while followed by the electrical resistance heating. For example, in the welding processes such as electroslack welding and the flash butt welding process, it is found difficult to classify under either of the two classes. It is difficult to put either under the arc welding processes or non-arc welding processes, because arcing is there for a short while, thereafter main heating takes place by the electrical resistance heating or by the joint is made by the forging and the plastic deformation. So, if you see here, as in case of electroslack welding process, this process starts with the arcing, and subsequently as soon as the sufficient pool of the molten flux is formed, the melting of the arc is extinguished, and melting of the base material edges takes place primarily by the heat generated due to the flow of current through the molten flux by the electrical resistance heating. So, in this case, arcing is mainly used for the melting of the fluxes. Once the sufficient pool of the molten flux is obtained, the arc is extinguished, and then by the flow of current through the molten flux, heat is generated by the electrical resistance heating, and which is subsequently used for melting of the consumable electrode as well as melting of the fin surfaces of the base material. While in case of the flash butt welding, the tiny arcs or sparks are first established between the components to be welded. Once these are established, a lot of heat is generated, even the cleaning of the edges to be joined it takes place, all impurities are removed from the surfaces, and once this happens, the forging pressure is applied between the components to be joined to get the metallic continuity. So, in this process also, the arcing the process begins first with the arc for a short while, thereafter forging pressure is applied to get the metallic continuity. Therefore, the classification of the welding processes based on the presence of arc or there is no presence of arc becomes difficult, because the processes like electroslack welding processes, electroslack welding process and the flash welding process cannot be put under any of the categories effectively, and therefore, such classification is also not found perfect. So, we will see that there are certain parameters based on which welding process can be classified, but each criteria is having some deficiency and not able to clearly put all the welding processes under the different headings. So, now we can conclude this presentation. In this presentation we have seen the various factors or the parameters based on which we can classify the welding processes. We have seen in detail that how can we classify the welding processes based on the use of the filler material or based on the use of the energy for developing the weld joint, or based on the whether the arc is being used or there is no arc in a welding process for developing the weld joint. So, further we have seen that each of these criteria is having the deficiency of one or other form and not able to cover or include all the welding processes effectively in a very justified manner under the each criteria. So, we will continue in the coming lecture, in the next lecture, to see that how we can classify the welding processes based on the other parameters also. Thank you for your attention.